Okay, this is the first of several planned short videos on problems involving Gauss's law for a variety of configurations of charge distributions. Some of these we've done in class. Some of these we have are done in the textbook, but they're, I think, important enough so that it'd be nice to have them on record somewhere so that you can refer to them. You're going to start off with a sphere, a non-conducting sphere that is charged with a uniform charge density rho, uh, and uh, the charge density rho, frequently this symbol is used to refer to charge per volume, so coulombs per cubic meter. We have a sphere, so it's natural that we are given a charge density, a charge per unit volume. And what we want to do is find the electric field for r greater than big R, the radius of the sphere, as well as r less than big R. So let's start off with uh, r greater than big R. We know because of the symmetry we're going to use Gauss's law. So we start off with a Gaussian surface. Here's the point R at which we're trying to calculate the electric field. So we'll start off with a Gaussian surface, a sphere of radius R, which is bigger than big R. And we write down Gauss's law. Here's the flux. Epsilon naught times the flux is equal to the charge enclosed. Of course, the next thing we're going to do is we're going to infinitesimalize this Gaussian surface by drawing a whole bunch of these infinitesimals of area delta A. And here's one typical delta A. Delta A is the outward normal. And at each of these delta A's, we're going to also indicate what the electric field is, the direction of the electric field. And the direction of the electric field, of course, is likewise radially outward. So E and delta A for each of these infinitesimal areas will be in the same direction. Furthermore, since because of symmetry, we can say that E has the same magnitude everywhere on our Gaussian surface. So in our summation, we can pull E out of the summation sign. You notice that our dot product just becomes E times delta A because the angle between E and delta A is 0. Cosine is 0 is 1. So we have the summation of delta A. The summation of delta A is our usual, since this is a sphere, the surface area of a sphere, 4 pi r squared is equal to the charge enclosed. And in this case, the charge enclosed is the charge per volume times 4/3 pi r cubed, which is the volume of a sphere. So doing the algebra, we end up with that E is equal to 4 pi's cancel, 4 pi's cancel. So we have rho r cubed divided by 3 epsilon naught r squared. So this is the electric field for r greater than big R. Just to check to make sure it's dimensionally correct, we have charge per volume, which is rho, multiplied by r cubed, which is the volume. So we have charge in the numerator, and we have an r squared in the denominator with an epsilon naught also in the denominator. So dimensionally correct. So that's the electric field for r greater than big R. What about for r less than big R? Well, here's my r now at r less than big R, so I'm going to draw a Gaussian surface, again a sphere of r less than big R, something like that. And I again do the same thing, draw a delta A vector, or infinitesimalize the area, draw a delta A vector, and for each of these delta A vectors I'm going to draw an E vector, like so. And again, E and delta A are in the same direction, so when I evaluate the flux through this Gaussian surface, I will have, again, E is constant, so I pull that out. Sigma delta A will give me again 4 pi r squared. But now this time on the right hand side, the charge enclosed, we only want that charge which is enclosed within the Gaussian surface, so only this charge in here. So that becomes rho times, our sphere has smaller volume now, 4/3 pi r cubed, little r cubed. So again, simplify, 4 pi's cancel, r squared cancels with that. So we have that E is equal to rho r divided by 3 epsilon naught. Again, we see that it is dimensionally correct, and we have an electric field that looks like this, which means if we were to plot the magnitude of the electric field as a function of r, and here's big R, we see that from 0 to big R we have a linear electric field. Electric field is linearly proportional to R. And then for R greater than big R, it'll be an inverse square law. Something like that. Okay, so that's the electric field due to a non-conducting sphere with uniform charge density.